each of the autocorrelation functions given below state whether the process.
Wait a second, 2-1? Or 1-2?
1-2 is just stating whether or not each process might be wide sense stationary or can't be. You're not really solving it, or maybe you are.
All right, well, I didn't even get to that. How about we do 6-1.1, my bad.
6-1.1, a stationary random process having sample functions of x of t has an autocorrelation function Rx of tau is equal to 5e to the negative 5 times the absolute value, like negative 5 tau.
Did we do this one?
Yeah, we did.
We did it? Does everybody know how to do this one? He's gonna have a z of t that's equal to x
When he has a y of t
or y of t.
is equal to x of t plus bx of t minus 0.1.
And they mentioned something here, it's equal to x of what?
T plus b times x of t minus 0.1. And then this is the one where you have to find the value of b that minimizes the mean square.
Forget finding the value of b. If you're given something like this, doesn't matter what it is, go straight to the definition of the autocorrelation function. So that ultimately, we have the autocorrelation of this. You all with me, class? And if you look at this, b can be anything. It can be 0, it can be 100, it can be anything. Now, one thing about an autocorrelation function, it has to be even. We'll see the properties in a second. And there will be some values of b that may not work so well. Anyway, when we get the expected value of y of t, well, sorry, the expected value of, and this would be y of t times y of t plus tau. The only thing you're going to do for this one, I hope everybody did this, is really just put by the definition, substitute in t and t plus tau for the arguments there, y of t, and then break it out. With me on this one? And if you do this, it's pretty straightforward. It's going to be the expected value here of x of t plus b times x of t minus 0.1, and then it's times x of t plus tau plus b times x of t plus tau minus 0.1. And the thing I'm trying to make clear is it's always going to be, when you're looking at these things to get an autocorrelation effect, it's always the difference between this argument and the other argument. It's multiplied and you get an expected value. That would define the autocorrelation process. So for this one, pretty straightforward. I look at this and I can see I have the expected value of x of t times x of t plus tau. Right below here, I'm going to just put that. Can everybody see that's the autocorrelation function? Just the autocorrelation function that's stated right there. So this becomes just 5e to the minus 5 absolute value of tau. Now, along that lines, when I take this times this, I'm taking its first, inside, outside, last. So when I multiply this times this, I'm going to get a b out in front. Does everybody see that? B is a constant, so you just pull it out in front of the expected value. Then if you look at this, it's the expected value of x of t times x of t plus tau minus 0.1, so that's the autocorrelation function, or it's going to be 5 times e to the minus is 5, and that's the magnitude of tau minus 0.1. With me? Because the difference between the argument here, x of t, this is the argument is t, and the argument here is t plus tau minus 0.1. So that difference would be tau minus 0.1. Does everybody follow me on this? Can you see it in the back? Okay. You got that? Then it's going to be plus, and now I do this times this, right? So that's x of t plus tau times x of t minus 0.1. First, I'm going to take the b out in front. And now I get 5e to the minus 5. It's times the difference, and that difference would be tau minus 0.1. Wait a second. No, it's actually tau plus 1. If you subtract, if I take t plus tau and subtract this from it, I get tau plus 1. Pardon me about that. And then finally, for the last one, the argument t minus 0.1, and it's going to be t minus 0.1 plus tau. That's simply going to be plus b squared times, and I better put this over here, and then it's going to be 5e to the minus, and it is just minus 5 times the absolute value of tau, because the difference between this and this is simply tau. I hope everybody follows me. I made that point last time, but I assume everybody sees it now, right? Right off the bat, if you get this, and I think everybody sees, when I want the value of the mean squared value of y of t, how do you get it real quick? What do? If this is, do y'all agree that this is the autocorrelation function, r, y of tau? Do you agree with that, everyone? So how do you always get the mean squared value? Tau equal? Zero, right? Do y'all follow me? I hope I'm not asking something you guys don't see clearly, because I was trying to make the point, this is critical. So the mean squared value of tau is 0, obviously. For this process, we're multiplying just y of t times y of t. Tau is 0, right? That's y squared, estimated value. If tau is 0, what is it by looking? Well, I got 5, and I got 5, so that's 10, right? And then if tau is 0, right? Then I have 5 times b, 5 times b, and that's, since that's an absolute value, so it's going to be 2 times 5 times b, or 10b, e to the minus, and this would be 0.5. Do you agree with this, class? Y'all follow me on this? And that's really it. And if I want, now something he doesn't cover in there, but how would you get, and we're going to talk about this in a second, average value. Now, you don't see it. Did anybody look at the next sections? Section 2? All right. This is perfect, because that's where I want to lead in from here. I wanted to talk about one of these problems and lead in like this. So, just looking at this, first, how do you see if it's a legitimate autocorrelation function? Second, how do you get the mean squared value? We covered that. How do you get the mean value of the process? The mean value of this process is 0, because as tau goes to infinity, you'll get the squared value of the mean. You'll see this in a second. It's 0 for this one. As tau goes to infinity, everything goes to 0. Does everybody see that on this one? It's exponentially dying. And there's a few other things we can see if we look carefully. So I want to put this, I'm using these slides because a lot of this stuff, if I try drawing it, it's not going to be that good. So let me go ahead and get this, get these slides. I want to go through it. And yeah.
So the last time that we did that problem in class, when you were looking for the value of b that minimized the mean square value,
You have to take a derivative.
yeah, so you just squared the expected like e of x squared of what we were given, not the
Not
t
y
plus-
of t. We had to take y of t times y of t minus tau. All right, now we needed to get that, right?
Well, last time you didn't do that.
No, didn't I do the autocorrelation? Autocorrelation is taking the expected value of y of t times y of t plus tau. I'm pretty sure I did that. Didn't I, class?
I've got it.
You did like the expected value of y of t squared,
Yeah.
and then expanded the polynomial. And
That's for the mean value, the mean squared value.
Yes.
That's not for, he wants the value of b that minimizes the mean squared value,
Yeah,
right? So you take the mean squared value, just set tau equal to
Okay.
0, right? That's the mean squared value, and take a derivative with respect to b. Now, I think in class I might have said the value that minimizes, not maximizes, but in either case, the only thing you have to do is take a look at the value that makes the derivative of that function, the autocorrelation function, when tau is 0. equal to 0, then you find the value of b that does that and plug it in if you want the actual value of b into the first
We did
function.
that because we weren't actually like looking for the autocorrelation function, it was just a.
Yeah, but we got the autocorrelation, I think, in
Yeah,
general anyway.
No.
Huh?
Yes,
Okay.
yes, yes.
All right. Okay, let me,
I think it was just kind of given to make the problem easier.
he gave you the autocorrelation of x of t,
Yes.
but he didn't give you the autocorrelation of y. You have to derive that from knowledge of x of t. All right, now, I get both of these. Okay. Somebody can see this. That didn't come on? When that comes up, I'm gonna ask you to dim the lights because I wanna make sure. All right, now class, everybody has access to these slides. Does everybody know that? They're on OneNote somewhere. Chapter 6 slides. By the way, I posted the entire solution manual, a Word copy of it, on OneNote this morning, if you look there, because I think chapter 6 isn't in the PDF version.
Yeah, I know.
I'm sorry about that, I didn't even know that until I looked today. But you have all of it now, so I wanna go through this kind of quick. This part, I think you know. So basically, we're talking about autocorrelation, enough of that. We have a random process x of t at 2 different times. Obviously, if it's wide sense stationary and ergodic, it's really the time difference that matters, t1 minus t2 or t2 minus t1. Enough of that. There's an example of an autocorrelation. If that's a random process and you do an autocorrelation, it's always a peak when there is no time difference. That's the value of x of t squared, the average value. It's the mean squared value of the random process. I think everybody's got that, right? Next, here's an example where things are more slowly varying, and you can always see the peak has to be at 0. Now, there can be more than one peak, but the absolute maximum or the maximum possible value has to occur at 0 or tau equals 0. And it can be periodic, but you can get several places where you're gonna get a maximum. For this one, I did this one in class. Do you remember this one? Here you have a random process, and x of t is a from 0 to 1. If t is 0 to 1, it's 0 else. And they say a is uniformly distributed, so figure out the value, expected value of that. And it was 48. But he has it from minus 12 to 12. The example I did was minus 10 to 10, I think. It wasn't the same numbers. It's the same principle. Y'all with me on this class? All right. Now, believe it or not, that kind of a problem right there, if I put it in terms of words and stuff, instead of actually mathematical statements are much better. And you try to work that thing, if you don't look at the examples, you can get confused. I'm telling you that right now, and you will see in section 2. Yes, sir.
So what exactly is that EX of t asking for, like in a word problem? Like what would it call that?
No, this is the autocorrelation function.
So it
But-
just has,
Yeah, but here, instead of putting tau, the autocorrelation function, he has T1 and T2 because he doesn't state whether it's ergodic or not.
okay.
If it's ergodic, in other words, the expected values in time are the same as the statistical values if you add the joint density function, stuff like this. If they are the same, then you can use, if it's wide sense stationary, you can go right to the statistical nature. Okay. We talked about autocorrelation autocorrelation of wide sense stationary function. The only thing that means is nothing, the standard deviation of mean, nothing changes with time. It's something that's always going to be the same regardless of time. And that's not quite true for everything that's a natural process, because the rotation of the earth, you get the dark side, light side, so there is some possibility of statistical differences in the long term, but not usually in the short term for anything earth-based. And I've never used to this date any kind of statistical variation of atmospheric parameters when I'm doing radar problems. It's the time of day we just take a snapshot of what's going on in the atmosphere, and we use those values. All right, this is the example that we were just talking about without the B. It has a tau 1, but it doesn't have a B there. You all see this? Ours was x of t and x, and then it was plus b times x of t plus, or minus 0.1, or plus 0.1, it doesn't matter. Here, there's no b, and the autocorrelation is given without any 5 in front of it. It's a straightforward thing. You'll notice tau is squared there, not magnitude. And this is sort of a work through of the whole thing and how to get the autocorrelation. And there's really not a whole lot to talk about here other than it should make sense to everybody what he's doing. Y'all with me on this? Did anybody look at these slides? I thought they were very well done and helpful. Now we did 6.1 and 6.2, 6.1, or 6-1.1, 6-1.2. And as far as I can tell, there's no questions about those, right? Y'all with me in class? I'm trying to move through this fairly quickly. Now, the next thing is properties of stationary and ergodic, wide sense stationary, he used the word stationary, processes and ergodic processes. And he's, I don't know why that popped that way, but the first thing is going to be that the mean squared value is always going to be evaluating the autocorrelation at 0. That's it. And I think everybody's got that down. The next thing is, it's got to be symmetric about 0, about tau equals 0. If it's not, it cannot be a legitimate autocorrelation function. He gives an example at the bottom there. Y'all see this, class? I want to make sure everybody can see this. If you want to pull up the slides, go ahead, you can notate it. Third thing, and it really, what this is saying is the maximum possible value has to occur at tau equals 0, but it can occur more than once. And that's just the way it's going to happen. For instance, if you had a function like a cosine of omega t, then what you would end up getting is something that would have a periodic frequency in the autocorrelation associated with that cosine variation. And you'll see this in some problems. Okay, now this is important. I didn't talk about this property. If you think about the autocorrelation's definition, it's x of t times x of t plus tau, right? Now, if you think about that, if it does have a DC component, no matter how far you go in tau, you're always going to have a DC component times a DC component, or you're going to get the mean value squared, and in the limit as tau goes to infinity, that is the mean value squared. It's x bar quantity squared, and he'll show you that. We'll do an example. So just mark that down. In the limit, as tau goes to infinity, Rx of tau goes to the mean value squared. There's a statement in one of these slides that says that, but I'm just telling you right off the bat. Now, if x of t has a periodic component, and the best example is the sine or cosine of omega t. Now, you know, like x of t is a cosine of omega t. Then the autocorrelation will have periodic components. It's that simple. And he gives you an x of t equals omega t, and if theta is uniform, or plus theta, if theta is uniform from 0 to 2 pi, that's the autocorrelation. By the way, I would expect everybody to be able to understand how that came about. If this is x of t, and I'm just going to ask you to listen to me. If this is x of t, and then I have x of t plus tau, a stays the same, cosine is the same. Now you get omega quantity t plus tau, right? So eventually I get something where I get cosine of, you can think of it as a, where a would be the argument omega t plus theta, plus b, and b would be omega tau. Does that make sense? If you get cosine of a plus b, that's cosine a, cosine b, minus sine a, sine b. You're going to use that proof all the time, or that more or less definition in communications. You'll be using this crap like you wouldn't believe. I mean, Dr. Tugman would probably teach most of you. I know him. He's known for the man that makes you understand trig identities like the back of your hand. Anyway, that would be the autocorrelation. We can prove that if you want. And one thing you can see if you plot that, it will be a maximum at 0, but it'll also be a maximum when omega tau is equal to, think about that, n pi, right? When n is 0, you get a max. If omega tau equals 180 degrees, you get a max, because it's going to be, or it's actually going to be a min, then you're going to get basically, you're going to get values that are minimum and maximum based on omega tau is equal to n pi. N would be an integer. Now this is important. X of t. If x of t is organic and 0 meaning there are no periodic components, which means that's useful to know. And you'll see most of this worked out in problems. Now, for ergodic processes, this is here, it says, the magnitude of the mean can be determined by ignoring any periodic components and letting tau go to infinity. Specifically, the value you will get is the mean value squared. And then we take a look at properties of the autocorrelation in general. Now these are just the autocorrelation function, not the transforms. The first is there are no flat regions. In other words, if you have, no flat tops in the peak value. There can't be something where you have like a peak value that's flat and then it just tapers off to 0. There are no vertical sides. You can't have something where you just have something outside of an impulse that's a vertical side, and no amplitude discontinuities. That's sort of saying the same thing. You can't have a discontinuous autocorrelation function. It's always monotonically increasing or decreasing. Everybody with me on that? Okay. Now these are just Fourier transform properties, and I think most of you are at least have been exposed to Fourier transforms to the point where you realize that delta function in time goes to something that's constant in frequency, that type of problem. All right, so then he asks, can this be an autocorrelation function? The answer is no. It has both vertical sides and a flat top. A flat peak, I might add. Not any portion, but a flat peak, and that's impossible. Okay? Now for this one, this is the one I really wanted to get your attention on. So notate this. If you have this function right there, a couple things that you have to see. First, if you look for the mean squared value, just set tau equal to 0. Do y'all follow me? And that means you're going to have 25 plus 16 plus 36. That should be obvious. You get 77. However, the mean value, now you let tau go to infinity, and you ignore the cosine term here. Anything that's periodic, that's varying with tau, periodically you ignore. You just looked at the DC component 36, and that would be the mean value squared, so you take the square root and get 6. it's obvious. One of the key things here is, it just tells you the magnitude of the squared value, so it could be a plus, could be a -6 for the actual mean value of the process. You all with me on this, class? That's important. It's ambiguous as far as the sign, but the magnitude's clear to me. Finally, the variance, well, if you get the mean squared, you got the mean value, you can get the variance, and you can basically get all the information you need from that. Now, where we're really gonna see this is interesting is not in the tau domain, but when we take a Fourier transform of that in the frequency domain, it's gonna expose a whole lot of information, especially spectral power or energy density in signals. And this is a lot of information to it. This is where some of the things I'm familiar with and deal with in radar. Oftentimes we have signals that we send out and retrieve, get it back. Some sent by us, others to confuse us, basically. We send these things, we catch it. Now, when we take a look at this signal, if we're sending something that's got a randomness to it, and we get a signal back, we don't actually do auto, it's called cross correlation. We take the signal received, and we do a fast time correlator with the signal sent. And we don't necessarily look in the time domain, but in the frequency domain, and we can find information about what's called the Doppler frequency. Are you familiar with Doppler? You've had ELEC, right? How many have had or are taking ELEC in here? All right, so Doppler frequency becomes important, but there's other things that are really important. And I might add, there's a lot of stuff with information theory. If you have signals, a signal that you pull out of the air and just catalog it, if you do an autocorrelation with this signal, it looks random as heck, looks like just gibberish. But if you do a fast time autocorrelation function and you see frequency peaks in the frequency domain, you'll know that there's something intelligent creating that. Something out there, typically either a communication system or a radar or both, that is in the vicinity and tells you right away there's somebody else nearby. It's something that's useful to keep in mind if you're working with the military. All right, and yeah, here he just says, no, this is only the magnitude. So if you don't look at the answers there, just looking at this process, right off the bat, I hope everybody can see what the mean squared value is. If tau equals 0, it's 36/4, or 9, right? Everybody should see that right off the bat. That's mean squared value. If you look at the average value, or the DC term, I should say, the DC value of the process, X, in the limit as tau goes to infinity, it's 25/6.25. Do y'all see that? Because in the limit, the tau squareds dominate. You can divide everything by tau squared if you want. And he's gonna have that's what he's gonna get. 4. Mean value is plus or minus. Wait a second. Hold on, I'm sorry, I said something wrong here. Yeah, when tau equals, no, I didn't. I take it back. When tau goes to infinity, I get 25/6.25. Yeah, that is right. Anyway, he's just working an example to show everybody how you would determine from that. Now this is tricky right here, so just give me a little bit of attention. When you look at this, determine the largest value of A for the following functions to be a valid autocorrelation function. All right, in this case, when you look at this, looking, it's hard to tell. Here's where you find the key, and you got to almost think this through. It's got to be symmetric if the magnitude of tau is in both of these terms. Do y'all follow me? If it's magnitude of tau, it doesn't matter if it's plus or minus. So yeah, it's symmetric. Any point higher than Rx equals 0, well, you don't know So the only way you find that is what, you can take a derivative and set it equal to 0. And by the way, I didn't say this, but Fourier transforms of any of these autocorrelation functions have to be greater than or equal to 0. They can't have negative components. That's just one of the things that happens with autocorrelation always. Anyway, for this one, if you look at it, how would you find out if there's any other point besides 0 that's a maximum? It's obvious. What do you always do? Take a derivative, right? In this case, if you take a derivative of this with respect to tau, I think he does this right. Yeah. He's going to get this equation, and then it's just an inequality. So he says 6a over 36 is less than 2 tau, and that means a less than 6 is required for that. Now that's one condition. You all follow me, class? He's just going through that. Would have to be less than or equal to 6. If it was greater than 6, and you went through this and actually plotted it, you would find a value of the peak greater than the actual value of tau equals 0. Then the Fourier transform. I think everybody knows how to take a Fourier transform of an exponential. And anytime you have that, like e to the minus a magnitude of tau squared, you're going to get an omega squared plus tau, or plus that coefficient a squared term, and then you're also going to get the a squared term on top. He just shows you this. Now, if you take a look at this, yeah, there's a 6, there's a 4. This is right. If you take a look at this, it's hard to see just looking at this if there are any values or what value of a would make this thing negative. And he goes through and he does an inequality there and finds a less than or equal to 6. And then he has the range, so it's a less than or equal to 6 dominates. Now this one is kind of weird. Take a look at this one just for a second. If the autocorrelation is 10 times e to the minus 4 magnitude of tau minus a, for any value of a except 0, it wouldn't have a maximum at 0. Can everybody see that? If you look right here at a, suppose a is 1. Well, e to the, think about this, tau minus a, when tau is 1, then I have e to the 0 here, which is 1. Any other values besides tau is equal to a, and it's going to be less than that, so that can't be a legitimate autocorrelation. These are just points he's making. I just want to bring your attention to this because you can, some of this stuff can get confusing. And this is true only if a is 0. Here's one that's a little weird. What if you saw that? Well, the first part right here, that does have a peak value. I mean, the 20 cosine of 5t. That is, in fact, legit. That's a legitimate autocorrelation. But this part is a sine. The sine of tau is a maximum at sine of theta is maximum at plus or minus 90 degrees, right? Or pi over 2 times that. And the only time this is going to work if a is 0. And the Fourier transform will be equal to or greater than 0 only if a is 0. Now this next part, I'm not going to spend a whole lot of time on this, but I want to tell everybody this. Here's where it gets confusing. Now if we have random binary waveforms, first, let me get to the point. You know, everything, just about everything we do for high-speed processing is going to be digital signal processing and digital image processing. Everybody at this point in your career should know that. You with me on this? What does that mean? Well, it means we're going to send ones or zeros in some way, shape, or form. Either non-return to 0, or we're going to take a signal and modulate it, and we're going to say that it's an FM signal. If there's a frequency F1, it's a 1. If it's an F2, it's a 0. We have some way of identifying only 2 states, 2 possible states. Now, we're gonna send these things over a data channel, and this is just the raw. He's talking about if we looked in time, what is being sent. Even though in the digital domain, this is a continuous time waveform, but in the digital domain, it would be like a 1 and then a 0, and it would be spaced a certain amount of time in between. Then nothing else is definable if it's true digital stuff, right? It's gonna have discrete values only for instances in time that are integer values of the time state. However, he's showing like the voltage level that would be there on a transmission line if we stripped off any of the high frequency carriers. And there's an element of randomness. Now, I gotta explain something. Here's where I have to spend more time on this, but he's gonna say there's a certain width to this that is always TA. Now, somewhere during this time, TA, either there's a transition, it goes from A to A minus, or it doesn't, which doesn't make a lot of sense. So it can go from A to A minus. In other words, this is just a plot of one particular statistical variation. So it says here's time, here's TA from here to here, and it can be an A or it can be a minus A. You all with me on this class? Then he talks about, but when does this waveform start? It's going to have a width of TA where it can statistically change. It starts at some value called, where there's going to be a T0 that's random. So TA is not random. It says in there it's going to change, but T0 is a starting time, and that's uniformly distributed from the beginning to the end of this. So TA could be negative, y'all follow me in this class, or T0 could be negative. And now you look at this, and what he tries to do, if he does he do it here? Yeah. He tries to show you, okay, that's a 0, a negative state. Here's a 1, there's a 0, there's another 0, so it didn't transition. And look, if this is TA here, this would be 2 TA. Can you all see this? This is the width TA. This is the width 2 TA. So in that period, it can either all be the same, or it can transition one time from the original state. He tries to give you an idea of what's going on. You got 1 or 0, 1, 0, 0, 1, 1, 0. Takes a little time to get through this. So let's see on a correlation of that and assume A is constant. And now it gets even crazier. I'll simplify this in a second, or try to at least. So he's just giving you more drawings and showing you that tau itself is a distance between any point in time t and any point t plus tau, anywhere over that pulse where the pulse exists. Can you all see how many different time constants? You got T0, TA, T, and tau, all to worry about. Now the nice thing is, a lot of this stuff just cancels, and here's the really nice thing. Have you noticed there's no 0 portions of this waveform? It's either A or minus A. That's nice. Something else about this, it says every time you get out of the range of TA in width, the expected value is 0. It's got a mean value of the process of 0. So x of t, if it's just this random waveform, has an expected value of 0, which really helps. If you have a non-zero mean, then this problem gets a little more ugly, a whole lot more ugly. So when he goes there, he's trying to show you what tau could be. It could be that small, or it could be that large. Now, when it's this large, if tau is greater than TA, statistically speaking, this point and this point have no statistical relationships. Y'all with me? You've gone through the period where a transition will occur, and that means the expected value is 0. It gives you the upper limit on that. However, in this one, just take a look at this. Can everybody see that they're very close? And as tau goes to 0, you're going to only get the mean squared value of that process, which will be a squared, by the way, because it can't be anything but that. So now you get down to this. How do you go about calculating the expected value? And I'm going to say this. You can do it by first getting rid of T0 completely. get rid of that, that thing's an annoyance. Don't do that. If you just take the waveform without T0 and take a look at, and I'll try to just draw this to you because I'm gonna love with you. You go through this stuff by yourself first time, you're gonna wonder, how are you gonna get this? Just leave the lights off. I wanna just show you this. So if you take a look at a process like this, and this one is nice, but I'm gonna make this A here, and I have, this would be T, call it X of T. Height would be A, call this X of T here. Right below it, I'm gonna show you, height here would be A, this right here would be minus A, and this is gonna be X of T plus tau. Now the only thing I'm gonna do is take that and shift it. So it's gonna be something like this. And this distance right here is going to be tau. Go with me? Now if you look at this, anything beyond, I'll put this value right here as TA. Whenever I take a signal and tau here is greater than TA, there is the actual expected value is going to be 0 because it's the expected value of the first process, which is 0, times the expected value of the second process. They're outside of the range of overlap. Follow me on that, class? Now, if you look at that, what I'm really talking about, if I look at the expected value of this thing over the region where it exists, a period, and let's do this. Call this the period T. Then I'm multiplying this times this, and the thing is, I can't go beyond this point because there'll be no statistical correlation out here. And really what you're going to get, when I multiply this times this, I'm going to get an A squared effect. You follow me on this, class? Either it's going to be minus A times minus A or plus A times plus A. So the magnitude's A squared. I'm not saying this exactly the way I want, but if you think about it, when they're both overlapping, I just get A squared with tau is 0. You follow me on this? When I start skewing it, now this part of the waveform is out of the picture, statistically speaking. You follow me? And when tau goes to a full period, the expected value is 0 after that point. So we end up getting is really, that's going to be the peak value, and that's going to be minus, and really it comes out to, actually I can just take it as T, as tau, tau over magnitude of tau over TA. Call it small t. It's hard to see this the way I'm drawing it. What you almost have to do is take this, and I've got rid of the T0 term because that term will confuse you, but just take this. Remember, here's the area of overlap in these two signals, and as you're moving them through each other, you're going to end up getting, the ideal is if they're superimposed on each other, you're going to get A squared as the expected value. But then as they move apart, this is negative times positive. That's going to be a minus A squared. It's going to subtract from the A squared. It's not coming out the way I want, but what I'm really saying is this thing moves through, all of a sudden, you're going to get something where some of the area will be, or the A, this times this will be negative A squared and be subtracting from the overall amount of area. And this is the waveform. Now, I'm not saying it exactly the way I should, but I know what I can tell you is if you look at R of X of tau here, it has a peak value of A squared, and it just does this, where this is going to be TA and this minus TA. Now this is something that just goes from a plus A squared to a minus A squared. I want to make one last point, and it's that it'll be shown better there, but there's a lot going on here. This T0 thing takes away from the simplicity of this calculation. But if you have a signal that does this, and say this is the original signal, but there's going to be randomness where this is TA, and this is the actual period T, and you can say that TA is going to be less than or equal to T over 2, something like that, where you limit its range and say it's uniformly distributed. Well, if you look at this and you skew just this waveform, and say it's got TA, and skew it this way, now look, the area, I'm trying to show you, the area of overlap is only going to be there. And remember, anything greater than T, the multiplied product out here and here, you get rid of. You're only looking at the expected value over one period. Follow me, class? Try to at least, before I get too much down the road on this. So now, what we're talking about when when the actual skew is 0, when tau, this would be tau. When tau is 0, the maximum value you get is going to be A squared times TA, right? But it's averaged over the period T. So now it's less than A squared peak value. Y'all follow me? And it will still have that same taper, but this will be skewed downward. I'll try to show you here. Sometimes I struggle for words to discuss exactly what phenomenon I'm getting at, but I'm going to tell you a lot of this stuff is overly complicated with too many things that are random there. He tries to show you the true nature, but you've got to start, just assume T0 itself is not random, and TA is going to have a randomness in it. So anyway, he's trying to show you the areas of overlap. And the next part is the critical part. If you look at this, now he doesn't overlay the two waveforms. I wish he would. But at the end of the day, that's the autocorrelation for this function. The key takeaway from this one is, remember, this thing's always got a magnitude of A. It's either plus or minus A. So if you have a logic system where you're always going to have either a plus or minus 5 volts being sent, this would be an autocorrelation function for that if there's randomness for the ones and zeros. You follow me? But if it's something that's 1 or 0, or 5 volts or 0, now it's going to be different. And especially, depends how the problem's stated, but what if the waveform alternates between A and 0, and there he shows you the value, and I gotta tell you this much, see how it's A squared over 2? He's assuming that the actual pulse width can have a maximum value of T over 2. T would be the period. There's a lot to this one. I'm going to have to forego this discussion until next time, but I'm going to ask you to read this now. I want to be dead honest with you. Section 3 is probably going to be more confusing than a lot of the stuff we've had in the last 3 weeks. So you need to be attentive to this stuff and do the problems. It can get very confusing, and you're probably not going to understand everything, but I'm going to ask you to try 6-3.1 through 6-3.4 after you read the section 6.3. And I'm going to say one last thing. This is the last difficult concept in this course. The Fourier transforms are going to be a breeze because I'll give you tables if you need them for looking at the spectral energy density, but you have to at least appreciate this because you're going to have to write some of these functions. Once you see the homework, you'll understand. Let's quiz time, so do me a favor, just spread your stuff out. I'll get your quiz in 1 second. You have digital, right? They never did, as far as I recall, the statistical nature of digital